Let's take a look at the greenhouse effect. And we will begin by considering the energy balance of the Earth. And the energy balance of the Earth is the idea that if we have the power absorbed by the Earth, then that must be equal to the power emitted by the Earth. And that has to be true as long as the total energy of the Earth system is a constant, which it should be. So let's think about each side of this. The power absorbed by the Earth. How could we find an expression for that? Well, where does that power that's absorbed by the Earth come from? It comes from the sun. So if here's the Earth, we have the incoming incident electromagnetic rays from the sun. Well, the total power that is incident upon the Earth's surface from the sun is equal to the solar constant times pi r squared. We saw that in the last video. But how much of that is actually absorbed? Well, the albedo tells us the fraction that is scattered. In other words, the albedo tells us the fraction that is not absorbed. So the fraction that is absorbed is 1 minus the albedo. In other words, the albedo of the Earth's surface is approximately 0.315. So the fraction that is absorbed by the Earth is 1 minus 0.315. In other words, 0.685. All right, so then the amount of power from the sun that is actually absorbed by the Earth is 1 minus the albedo times the solar constant times pi r squared. All right. Now, what about the power emitted by the Earth? Well, the power emitted by the Earth would be easy if we had a black body. If the Earth were a black body, it would just be sigma a t to the fourth. However, the Earth is not a black body. It's approximately a black body. Maybe we can approximate it that way. But we're going to stick an emissivity in there. Remember, the emissivity is that factor that we can include to sort of adjust for the idea that things are not perfect black bodies. So the power emitted by the Earth is the emissivity of the Earth's surface times sigma times A, the surface area of the Earth, times T to the fourth power, where T is the surface temperature of the Earth. Okay, well, now we're getting somewhere. Now we have an expression. 1 minus the albedo times the solar constant times pi r squared is equal to the emissivity times sigma times A T to the fourth. And A, remember, is the surface area of the entire Earth, so we can replace that with 4 pi r squared. And then we can cancel out a pi and an r squared on each side, and let's see, let's stick some numbers in there. Well, the albedo of the Earth's surface is approximately 0.315. The solar constant is 1360 watts per square meter. Stefan Boltzmann constant is a constant, we know it. The emissivity of the Earth's surface is approximately 0.95. So if we solve for the temperature of the Earth is 256 Kelvin. All right, good job, right? No, that's a terrible job. The temperature of the Earth is not 256 Kelvin. That would be about negative 17 degrees Celsius. That is wrong. That is not the temperature of the Earth's surface. That's not the average temperature of the Earth's surface. That's far colder than the average temperature of the Earth's surface. The real average temperature of the Earth's surface is about 288, 289 Kelvin. So what did we do wrong? We seem to have included everything. We did this wonderful energy balance. We have all these values. What's wrong? The thing that went wrong is that we did not include the atmosphere. We completely ignored the atmosphere in our energy balance equation. You cannot ignore the atmosphere if you're going to consider the Earth system in an accurate way. The atmosphere of the Earth ends up increasing the temperature of the Earth's surface. So how can that be? How would it do that? Well, let's think about what the atmosphere of the Earth really is made out of. The Earth's atmosphere is about 78% nitrogen molecules, about 21% oxygen molecules, about 0.9% argon, and then there's trace amounts of other stuff. Now, the nitrogen molecules, the oxygen molecules, and the argon, they have essentially no effect on the incoming solar radiation or the outgoing Earth radiation. They are, in essence, transparent to the incoming solar radiation and the outgoing Earth radiation. It's the trace amounts of the other gases that make the difference. So the trace amounts of other gases, well, that includes things like neon, helium, krypton. So these are noble gases that don't bond to anything. And then there's also water, carbon dioxide, methane, and nitrous oxide. And those four just happen to be a type of gas called greenhouse gases, or GHGs. Greenhouse gases are defined as gases which absorb and emit infrared waves, but not other parts of the electromagnetic spectrum. Now, this has been something that has been observed since the 1800s. Um, but why? Why do these gases absorb and emit infrared light, but not the others? Well, turns out all atoms and molecules absorb and emit specific wavelengths. If you haven't seen that already, you should see it when we talk about atomic physics later on in topic E. But one explanation or one way to discuss this or explain this is that we can model a molecule as atoms which are connected by chemical bonds, and those chemical bonds behave like springs. Now, they're not literally springs. If you look at a molecule, you won't actually see tiny little springs in there, but we can model it that way. So, for example, carbon dioxide, we can model it as one carbon atom connected to two oxygen atoms on either side by little springs. And if we have incoming electromagnetic radiation at just the right frequency, it can be absorbed by this molecule. And it's a little bit like resonance. So imagine you have an incoming wave and it causes the little atoms to oscillate. If the incoming wave causes them to oscillate at just the right frequency, it can be resonance, or it can cause resonance in the oscillation of the molecules, or the oscillation of the atoms within the molecules. And the springs can also lose energy by emitting light of that same frequency, of that resonant frequency. But one thing to recall, and one thing that's going to be important in a moment, is that it's going to be re-emitted in a random direction. So the molecule can absorb incoming light if it's of the right frequency, but if it emits the light, it will emit it not back in the same way that it received it, but in any direction. All right. Now, I'm going to draw two black body diagrams here. So here's an intensity axis, here's a wavelength axis. The sun has a surface temperature of about 5800 K. So if we were to draw the black body curve for that, it would look something like this. And the peak of emission is in the visible part of the spectrum. So what that means is that most of the sun's emitted light is in the visible part of the spectrum. For the Earth, it's a little different. The Earth has a much lower surface temperature, like 289, 290 Kelvin or so. So it emits mostly in the longer wavelengths. It emits almost completely in the infrared part of the spectrum. So that's important. The sun emits mainly visible light, and the Earth emits mainly infrared light. So now let's put that together. Here's a diagram of the surface of the Earth, and let's put the top of the atmosphere here. And I'm going to draw the incoming solar light, the incoming visible light from the sun. So it comes in, about 31.5% of it is reflected, some by the clouds, some by the surface, and then 68.5% is absorbed. All right. Now, what about the infrared light that's emitted by the Earth? Well, the infrared light that's emitted by the Earth, here we go. And if there were no greenhouse gases, it would just leave the Earth system. But there are greenhouse gases in the atmosphere. There's water, there's carbon dioxide, there's methane, there's nitrous oxide. That outgoing infrared light from the Earth is absorbed by these greenhouse gases. And then that infrared light is then re-emitted by those gases in all directions. Now, some of it goes out off into space, but some of it, when it's re-emitted, is sent back down to the Earth's surface. So the greenhouse gases absorb some of the infrared light from the Earth that's emitted by the Earth, and then they re-emit it back down to the Earth. This is then absorbed by the Earth, and that is another source of thermal energy to the Earth's surface. So the Earth's surface, therefore, has a temperature that is greater when greenhouse gases are present than if they weren't. This idea is known as the greenhouse effect. And the greenhouse effect in itself is not bad. It's actually a great thing for the Earth. Because if there were no greenhouse gases in the atmosphere, if there were absolutely none, then the temperature of the Earth would be what we got when we used the simple energy balance. The temperature, the average temperature of the Earth, would be about negative 17 degrees Celsius. So without the greenhouse gases, the Earth would not be a good place for us to live. Now, before about 1750, the concentration of greenhouse gases in the atmosphere was, well, for carbon dioxide, it was about 280 parts per million, meaning that for every million molecules in the atmosphere, about 280 of them were carbon dioxide. Currently, the concentration of carbon dioxide in the atmosphere is about 410 parts per million, and it's rising every year. For methane, before about 1750, the concentration was about 700 parts per billion. It's currently about 1900 parts per billion. So the increase in carbon dioxide and methane in the atmosphere is caused by human activity. The increase in carbon dioxide and methane over the past few hundred years is caused by human activity. It's caused by burning fossil fuels, so burning coal, oil, natural gas, and it is also caused by deforestation. Deforestation causes an increase in carbon dioxide in the atmosphere because if we have fewer trees and plants, then there are fewer things which are absorbing carbon dioxide from the atmosphere. If you remember back to photosynthesis, the process of photosynthesis takes carbon dioxide out of the atmosphere and then through chemical processes turns it into essentially plants. So without forests, there's going to be more carbon dioxide in the atmosphere because there's not as many plants to take the carbon dioxide out of the atmosphere. So if the concentration of greenhouse gases in the atmosphere increases, then we would expect that more infrared light will be sent back down to the Earth. The greenhouse effect will be enhanced. Therefore, we would have a higher temperature on the surface. This is known as the enhanced greenhouse effect. It is also known as the anthropogenic greenhouse effect. Anthropogenic meaning human-caused greenhouse effect. Now, the exact implications for the Earth system are rather complicated. The Earth system is an insanely complicated system, so it's difficult to predict it in detail. But there are some things that we can say. There are feedbacks in the system, and I'll give you a couple examples of them. One example of a positive feedback, and I say positive in sort of a general sense, not in a judgmental sense, but one example of a positive sense is the ice albedo feedback. So if the average temperature of the Earth increases, then we would expect there to be less ice cover on the Earth, right? The polar ice caps would melt, the glaciers would melt, which means that the albedo of the Earth's surface would, on average, decrease, which means that there's an increase in the amount of solar radiation that's going to be absorbed by the Earth, which means that the temperature of the Earth will increase, which means there's less ice cover, which means the albedo decreases, which means the increased solar absorption and greater temperature, and so on. So we get an increase in temperature that just feeds back on itself in a positive way. Another example of a positive feedback would be ocean warming. So if the temperature of the atmosphere increases, we would also expect the temperature of the ocean to increase. If the temperature of the ocean increase, then it turns out a warmer ocean cannot absorb as much carbon dioxide. And that has to do a little bit with biology, a little bit with chemistry. But believe me, if the warmer ocean exists, then there's less carbon dioxide that can be absorbed from the atmosphere. So that means that there will be more carbon dioxide in the atmosphere, which means a greater greenhouse effect, which means an increase in temperature. And we're back to that positive feedback. Now, there are examples of negative feedbacks that have been proposed. So, for example, the carbon fertilization feedback. This is the idea that if we have more carbon dioxide in the atmosphere, we'd expect more plant growth. And if there's more plant growth, we'd expect those additional plants to take more carbon dioxide out of the atmosphere, which would sort of counterbalance the increase in the carbon dioxide in the atmosphere. Unfortunately, this is not observed. People have been looking for this, and it's really not a big effect. So this is not an example of a feedback that we really see happening in the Earth atmosphere. Another example of a negative feedback might be the cloud albedo feedback. So if the temperature of the Earth increases, or excuse me, the temperature of the atmosphere increases, then we'd expect more clouds to exist in the atmosphere. And that would increase the albedo of the Earth, which means that there would be less light absorbed by the Earth, which means the temperature should go down. Unfortunately, this is not observed. The cloud albedo feedback is not enough to stop the increase in the temperature of the Earth's surface. So, what are the implications of all of this? Well, as I said, the Earth system is very, very complicated, and that's a very difficult question to answer in a simple way. But what we can say is that the Earth's surface temperature in the future will depend on fossil fuel use. It will depend on our current and future fossil fuel use. So, for example, if we do nothing different, if we follow a business as usual model and we keep burning fossil fuels, then the expectation is, according to the best models that we have, that the increase in the average temperature of the Earth by the mid 21st century would be 3 to 4 degrees Celsius, which is about 5.5 to about 7.5 degrees Fahrenheit. Now, that's averaged over the entire Earth's surface. We'd expect there to be exaggerated increases in the temperature at the poles, but no matter what, we would also expect severe damage to ecosystems, damage, even destruction of entire ecosystems, which are designed, which have evolved to exist at very specific temperatures. And if we change those temperatures, those ecosystems will suffer. We also expect damage to agriculture, which depends on certain surface temperatures. And also, the increase in the temperature will cause destructive storms, heat waves, droughts. There will be changes in weather and climate patterns. We'd expect rising sea levels due to the expansion of water. Turns out that when water heats up, it expands. And also, the sea level will rise because of the melting glaciers and the ice on the land. So, what will happen if we limit or stop fossil fuel emissions? Will that solve the problem? Well, yes and no. With the current levels of carbon dioxide and other greenhouse gases in the atmosphere, it is likely that we will have about 1.5 degrees Celsius increase in the average surface temperature of the Earth by the mid 21st century. That's about almost 3 degrees Fahrenheit. That is going to damage the ecosystems on the Earth. That is going to damage agriculture. That is going to cause an increase in storms, heat waves, droughts, change weather and climate patterns, increase sea levels. However, this would not be as damaging as a business as usual situation. Now, clearly, this is an important topic. It is a deep topic that involves physics, biology, chemistry, economics, sociology, all kinds of subjects. And I'll provide a couple of links, but I hope this has given you a little bit of perspective from the physics side.